Hi all. In this lecture what we will start with, we will first start with the power system matrices. These are the matrices which are used to represent a power system. There are various representations of power system, like we saw the case of a single line diagram, and if that single line diagram is represented in terms of matrices, then it is called as a power system matrix. Now usually there are two type of power system matrices. One is your Y bus matrix, which is also called as bus admittance matrix. Other is your Z bus, which is called as bus impedance matrix. Now what is the physical significance of these two matrices? Y bus is used for load flow analysis. Now first thing that comes to mind, what is meant by load flow analysis? Now as you can understand, the term load means power, the power drawn by a load. Load flow analysis focuses its attention on the flows in the transmission line or the current flows in the line, what is the voltage at each and every bus, what is the angle of the voltage, and what is the different type of power, that is the generated power and the demand power. So load flow analysis basically involves finding the steady state solution of the power system at each and every bus. Now if you wish to determine the bus voltages or the node voltages, then we usually perform nodal analysis, and to perform nodal analysis we require the Y bus matrix or the bus admittance matrix. Similarly, Z bus is used for fault analysis. Now what was the fault analysis, since we covered it earlier? Fault analysis means we have to determine the fault current when there is a fault on any bus in a power system. So up to now what we have seen is we can calculate fault current directly, like for a symmetrical fault like this. We find the equivalent impedance, then equivalent plus ZF. Now in using Z bus, we have to identify what is the Thevenin impedance from the matrix. So that is the challenge by doing the fault analysis using Z bus matrix. Okay, so Y bus and Z bus are two alternate representations of the same power system network. So let us see an example how to do the nodal analysis on a power system network. Now suppose this is the power system network. This node I consider as reference or ground. So this is marked as 0. So Y10 here represents the admittance between node 1 and node 0. Y20 represents the admittance between node 2 and node 0. Y30 represents the admittance between node 3 and node 0. Similarly, Y12 is the admittance between 1 and 2. Y23 is the admittance between 2 and 3. Now how to write the KCL equation or the nodal equations? First we will assume the voltage at each bus. V1, V2, V3. Now when we are writing the nodal equations at node 1, we will assume all the currents as outgoing currents like this and this. Now current always goes from higher potential to lower. So this current in Y12 will be V1 minus V2 into Y12. Okay, or we can say V by Z or V into Y. The current in Y10 will be V1 into Y10. This is the outgoing current. What is the incoming current? I1. Now if we write the KCL equation at node 2, again we will assume all the outgoing currents. Currents will be like this. So it will be V2 minus V1 into Y12 plus V2 into Y20 plus V2 minus V3 into Y23. Now since there is no incoming current, this will be 0. Now if you might be wondering how I am writing this term, because potential of this node is 0. So you can write it like V2 minus 0 into Y20. At node 3, we will again assume outgoing currents like this and this. So it will be V3 minus V2 into Y23 plus V3 into Y30. And the incoming current is I3. Now if we simplify these equations, then what will be the first equation? It will become I1 is equal to Y10 plus y12 v1 plus minus y12 v2. If we simplify second equation, it will become 0 is equal to minus y12 v1 plus y20 y12 y23 v2 minus y23 v3. And the last equation on simplification will become I3 is equal to it will be minus y23 v2 plus y30 plus 23 v3. Now if we write these equation in matrix term, then the left column vector will be I1, then 0, then I3. And the right column vector will be v1, v2 and v3. We need to find a matrix between these two. Now this matrix will be, first element will be y10, y12, second minus y12, third will be 0. Similarly, minus y12, this element, then this. So if we write the matrix, it will directly be y10 plus y12 minus y12 and then 0. And here it will be minus y12 y20 y12 y23 minus y23. It will be 0, then minus y23 y30 plus y23. Now this matrix is called as bus admittance matrix Y bus. This represents the relationship between the bus current and the bus voltage. Now what is meant by bus current is, bus current represents the external current source which injects the current at each and every bus. Like I1 is the current source at bus number 1, I3 is the current source at bus number 3. So these are the external current sources at each and every bus. Okay. So remember this point, bus current is nothing but the current injected at each bus. And what is voltage at each bus? That is called as V bus. That represents the nodal voltage at each and every bus. And the relation between these two is given by the bus admittance matrix, that is your Y bus. So what I can write down is, in matrix form I can write down I bus is equal to Y bus into V bus. Now if you multiply both sides by Y bus inverse, this will be V bus, or we can say V bus is equal to Z bus into I bus. So that means the bus impedance matrix is equal to Y bus inverse. Okay. These relations how I am directly writing is because by Ohm's law we can say V is equal to I into Z or I is equal to V into Y. So here Z bus and Y bus follow the inverse relationship. These two matrices are inverse of each other. And remember, both the matrices are symmetrical in nature. So you can remember this identity, that inverse of a symmetric matrix will yield another symmetric matrix. Now let us understand what is the physical significance of each and every Y bus element. So first thing that you must understand is small y. This is used to represent any admittance, and capital Y represent element of Y bus matrix. Okay. So these two are the general notations. So if we write the equation in matrix form, it will be I1, I2 up to In. Here, these represent the current sources at each and every bus. So remember, if you are forming the nodal equations, then you have to convert each voltage source into current source before forming the nodal equations. So this is your n buses where there are n sources. So Y bus will have an order of n cross n. And here we will have n bus voltages V1, V2 up to Vn. The matrix will be something like this: Y12 up to Y1n, Y21, Y22 up to Y2n, yn1, yn2 up to ynn. Okay, these y's represent the elements of the y bus matrix, whereas small y is used to represent the admittance connected between the two buses or between the bus and the ground. Now many of you might be wondering how come there is the admittance between a bus and a ground. That may lead to a short circuit fault. Not at all. That admittance is present due to the line charging capacitance. If you represent any transmission line by a pi model, then there are admittances or there are capacitances on both sides of the impedance. That is your shunt admittance, or that is the admittance between any bus and the ground. Okay. So it doesn't mean that we have connected a transmission line between the bus and the ground. Rather, it is the shunt element of the pi model. Now if we write these equations, if we expand this, then it will become I1 is equal to Y11 V1, Y12 V2, Y1n Vn. Or we can say any current II will be Y11 V1, Y12 V2, YII VI, YIJ VJ plus YIN Vn. Now if I want to find YII from this equation, what is the method? You just equate all the voltages to 0 except Vi. Then all these terms will go to 0. What will remain is YII into Vi. Then YII will become II upon Vi when all the voltages where J is not equal to I are 0. So this represents driving point admittance, that too under short circuit, because voltage 0 implies that the element is short circuited. Similarly, if we wish to find Yij, then you have to equate all the voltages to 0 except Vj. So it will be II by Vj when all voltages are 0 except K is not equal to J. So since there is a current at one bus and the voltage at the another bus, this will be transfer admittance under short circuit. So this is the physical significance of the Y bus elements. Yii represents the diagonal element, Yij represents the off diagonal element. That means the diagonal elements of the Y bus matrix represent the driving point admittance under short circuit, and the off diagonal elements represents the transfer admittance under short circuit. Now if we compare this matrix to the matrix that we derived earlier, what was the matrix that we derived earlier? The matrix was somewhat like this. Then minus y23, y30 plus y23. So if you see the diagonal elements are basically sum of all the admittances connected at that bus. If you see the circuit that we used here at bus 2, what are the admittances connected? Y12, Y20, Y23. Then Y22 will be sum of all these admittances. Okay. Similarly, at bus 1 we have two admittances, Y10 and Y12. So Y11 will be the sum of these two admittances. Similarly, at bus 3 we have two admittances, Y23 and Y30. So at bus 3 Y33 will be sum of these two admittances. And the off diagonal elements are negative of the admittance between the two nodes. That means if you see Y12, it was minus Y12. So negative of the admittance between the two buses. So what I can generalize is Yii is equal to sigma j is equal to 1 to n Yij, where Yii will be actually, or we can say rather go from 0 to n, where j is not equal to I. So it will be like yi0, yi1 up to yin. And remember, if two buses are not connected with each other, like in the example that we took, bus 1 and bus 3 were not directly connected. That means there is open circuit between those two buses. If there is open circuit between those two buses, the impedance is infinite or admittance is 0. That is why this element between bus 1 and 3 is 0. Okay. So whenever two buses are not connected, the element or the admittance between those two is 0. Similarly, I can write Yij is equal to negative of the admittance between the two buses. Okay. So that is how we can directly determine the diagonal and the off diagonal elements of the bus admittance matrix. So remember, diagonal elements are sum of all the admittances connected at that particular bus, and off diagonal elements are negative of the admittance connected between the two buses. Next, let us understand what is meant by elements of each and every Z bus. Now in Z bus, what is the matrix that will be formed? V1, V2 up to Vn, where V1, V2, Vn are bus voltages and I1, I2, In are bus current. Again, what was the bus current? The current injected at each bus. The element will be Z11, Z12 up to Z1n, Z21, Z22 up to Z2n, Zn1, Zn2 up to Znn. So we can say that V1 is equal to Z11 I1, 12 I2 up to 1n In. That means if I write Vi, general voltage, Zi1 I1 plus somewhere Zii II, Zij Ij plus Zin into In. Now again, if we wish to determine Zii, that is the diagonal element of the matrix, and Zij, that is the off diagonal element. So how to determine Zii? If you wish to determine Zii, equate all the currents to 0 except Ii. So it will be Vi by Ii. Given that Ij is equal to 0, J is not equal to I. So it represents impedance V by I, and since both are on the same point, it is driving point impedance, and since currents are equated to 0, it is under open circuit. Similarly, if we want to find Zij, then we have to equate all the currents to 0 except Ij. K is not equal to J. So this will be actually transfer impedance under open circuit. Okay, so that is the diagonal elements represent diagonal elements represent driving point impedance, and off diagonal elements represent the transfer impedance. But remember, Zii is not equal to 1 upon Yii. Why? Because elements of the bus admittance matrices were defined under short circuit condition, and elements of Z bus matrix are defined under open circuit. So though the formula of these two seems reciprocal of each other, but the conditions are different, and hence both cannot be represented as reciprocals of each other. And if you see, if you might have studied Thevenin, or you went through the Thevenin, in Thevenin's theorem what we do is we open circuit all the sources and we short circuit all the voltage sources. Then whatever is the impedance, or whatever is we supply a voltage source at any point and we find the current through it. What I am saying is, you open circuit all the current sources, then apply a voltage source at one bus, and find the current through it, the ratio of those two will give you Thevenin impedance. Similarly, if you see this equation, I have opened all the current sources, then I have taken the ratio of voltage and current at a single node. So this is supposed to give me the Thevenin impedance at bus number I. Okay. So that is how it is used in fault analysis, because diagonal elements of the Z bus matrix are the Thevenin impedance at that bus. And as I told you, in the fault analysis, to find the fault current, we need the Thevenin impedance and the fault impedance. Fault current is equal to EF by Z Thevenin plus ZF. Okay, that is how. Now let us understand how to derive the Y-bus matrix. First, let us understand some properties of the Y-bus matrix. Y-bus is a symmetric matrix. That means upper triangular and the lower triangular matrices are same. Now how does that help us is, if you are saving a Y-bus in the memory of a computer system, then you only have to save half the number of elements, either the upper triangular or the lower triangular, plus the diagonal elements. That is, in a n cross n, let us say in a 10 cross 10, there will be 100 elements. Out of this, 10 will be diagonal. So you have to save this 10 elements. Out of other 90 elements, you have to save only 45. So that means 45 plus 10, total elements that we need to save is 55. So almost 50% of the elements only I have to save in the Y-bus matrix. So that saves a lot of memory. Other property is Y-bus is a sparse matrix. Sparse means most elements are 0. Now how most elements are 0? As I told you, whenever two buses are not connected to each other, the admittance between them will be 0. Now in a practical power system with hundreds and thousands of the buses, there is a higher chance that one bus is connected to 2, 3, 4 buses, or let us say 10 buses, but not to the other 100 buses. That is why most of the elements in Y bus will be 0. So that further saves our effort. If most of the elements are 0, then the number of elements that I have to save will be even less than 55. So that saves a lot of computer memory and eases our computation, as most of the elements are 0. But this is not the property with the Z-bus matrix. Z-bus matrix is a full matrix. Very less elements or almost no element is 0, because 0 elements represent short circuiting. Hence, all the elements will be non-zero in a Z-bus matrix. Now this sparse property is represented by sparsity of the matrix, where percentage sparsity is number of 0 elements by total number of elements. Okay, let me take an example. Suppose I take a power system with 20 buses and 30 transmission line. Okay, now each transmission line will have some impedance Z and some admittance Y. Okay, so if transmission line connected between bus 1 and 2 has the admittance Y12, where it will appear Y12 will be equal to minus Y12, and by symmetry Y21 will be equal to Y12 equal to minus Y12. Now due to one admittance, two elements of the Y-bus matrix are non-zero, that is Y12 and Y21. So due to one admittance, Yij is equal to Yij is equal to minus Yij. So one transmission line yields two non-zero elements. That means 30 transmission line will yield 60 non-zero element. Is it fine? And all the diagonal elements are always non-zero. Why? Because diagonal elements are sum of the admittances at that bus. Now if a bus is connected to a power system, there will be at least one transmission line through that bus, and if there is one transmission line to that bus, then there is one admittance connected to that bus. So sum of all the admittances will be non-zero. Sum of all the admittances can be 0 in only one case, where no admittance is connected to any bus. In that case, that bus itself does not form a part of the power system. So we have 20 non-zero elements as they are diagonal elements and 60 non-zero due to 30 transmission line. So we have 80 non-zero elements and the order will be 20 cross 20 n cross n, which means 400 elements. So what is the number of zero elements? 400 minus 80, that is equal to 320. So what is the percentage sparsity? 320 by 400, that is equal to 80%. Okay, that means only 20% of the elements are non-zero, 80% of the elements are zero. Now what is meant by direct inspection method is, by looking at the circuit topology or the network topology, I can form the Y-bus matrix. How? Because I know the diagonal elements are sum of all the admittances connected at this bus and off diagonal elements are negative of the admittance between the two buses. Thus, just by looking at the network, I can form the Y-bus matrix. Okay, and remember, in Y-bus, sum of row elements, if you sum each row, then you will get yi0, that is the admittance between bus and the ground. Okay, like if you see in the first example that we took, the first row was y10 plus y12 minus y12 0. If you sum it, you will get y10. That is the admittance between bus 1 and ground. If the bus 1 is not connected to ground by any admittance, then the sum will be 0. It is non-zero only if there is an admittance between bus and ground. So whenever you are asked about the admittance between bus and ground, you will just sum up that row. The next method to construct Y-bus is called as singular transformation method. Now what is the disadvantage of the direct inspection method is that it does not take into consideration the mutual impedance between the transmission line. Now when we were studying transmission line, there we saw whenever a transmission line carries a current, it produces a flux which can link another transmission line and hence causing mutual inductance. So it does not take into account the mutual impedance between the two transmission line. It only considers the self admittance of a line and the admittance between the bus and the ground. But what if two transmission line have some mutual impedance or mutual admittance? Then we need to move on to the singular transformation method. Now in this method, what we do is, we will take a power system network, let us say having a 4 buses 1, 2, 3 and 4 as marked here, and there are 6 transmission line marked as 1, 2, 3, 4, 5, 6. First we will form a directed graph. Now what is meant by directed graph is a graph in which each branch has a certain direction. Like this branch is going from 1 to 2, this from 2 to 3, this from 3 to 4, 2 to 4 and 1 to 4. So that is an example of directed graph. Now what we do is we form the bus incidence matrix which has the order b cross n, where b is the number of branches, n is the number of nodes. So here 6 branches are there and 4 nodes, so 6 cross 4. So first let me form the matrix. Okay, the horizontal row represents the row, this is the nodes, this is branch. Now first branch at first node. The first branch at first node is outgoing. If it is outgoing, the element will be plus 1. First branch at second node. This branch is not connected to this node, so it will be 0. First branch at third node, it is not connected, so it is 0. First branch at fourth node is incoming, so it is minus 1. So any outgoing branch at a node is represented by plus 1, incoming by minus 1, not connected by 0. Similarly, branch number 2, it is between 2 and 3. So this will be 0, this will be 0. It is outgoing at 2. Sorry, it is between 2 and 4. It is outgoing at 2 and incoming at 4. So plus 1, minus 1, and it is not connected to 3. Now branch number 3 is between 3 and 4, outgoing at 3, incoming at 4. So 1, minus 1, this will be 0. Then branch number 4 between 1 and 2, 1 minus 1, 0, 0. 5 between 2 and 3, 0, 1 minus 1, 0. 6 between 1 and 3, that is 1, 0, minus 1, 0. So that is your bus incidence matrix. Okay. So remember this matrix, how to form it. If any branch is going outwards, it is taken as plus 1, incoming is minus 1, and not connected is 0. Now any element, when we want to do the nodal analysis, can be represented like this. There will be some external current source, let us say J. This will be the admittance Y, and there will be some branch voltage, that is voltage across each impedance, that is V. If current is I here, this is J. So I can say I plus J is equal to Y into V, where this is the branch current flowing in the branch having admittance Y, and V is the branch voltage. So I can say I branch is equal to Y into V branch. But actually I need the relation between the I bus and V bus, because that will give me the relation as Y bus. So I have to convert this relation into I bus and V bus. That means we need to convert the branch currents and the branch voltages into bus current and bus voltage. Now if you see here in this network, first let us convert branch voltage into bus voltage. Now what is the voltage of branch 1? It is actually V1, V4, V2, V3. So branch 1 voltage is V1 minus V4. Branch 2 voltage is V2 minus V4. 3 is V3 minus V4. So what I can write down is VB1 is V1 minus V4. VB2 is V2 minus V4. VB3 is V3 minus V4. Similarly, branch number 4 was between 1 and 2. So it will be V1 minus V2. Branch 5 was between 2 and 3. V2 minus V3. 6 was between 1 and 3. Vn minus V3. How I am choosing which one to subtract from which one? That depends on the direction of branch. If it is going from 1 to 2, I am taking V1 minus V2. Now if we write it in matrix terms, it will be V1 minus V4 okay. Here we have a matrix 6 cross 1, that is VB1 to VB6. This is 4 cross 1, so this matrix will be 6 cross 4. Okay, first is V1 minus V4, that means 1, 0, 0, minus 1. V2 minus V4, that is 0, 1, 0, minus 1. Okay, V3 minus V4, 0, 0, 1, minus 1, 1, minus 1, 0, 0. V2 minus V3, 0, 1, minus 1, 0. V1 minus V3, 1, 0, minus 1, 0. This is actually the bus incidence matrix, that is A. So what I can say, V branch is equal to A into V bus. Okay, so that is how we can convert the branch voltage into bus current. Bus voltage. The next challenge lies in converting the bus current or branch current into bus current. Now, the sum of the currents that are going in different branches at a bus will give me the bus current. That means, what is the bus current at I1? It will be equal to IB6, IB4 and IB1. So by KCL, I1 is equal to IB1 plus IB4 plus IB6. So let me form such kind of equations. First is, what is bus current at 1? IB1 plus IB4 plus IB6, because all branches were outgoing. Then what is the bus current at 2? In 2, the branch 4 was incoming, 2 was outgoing and 5 was also outgoing. So IB2 minus IB4 plus IB5. In bus number 3, the branches that were incoming was 5 and the outgoing was 3. 5 and 6 were incoming, 3 was outgoing. So IB3 minus 5 was incoming, 6 was also incoming. And what is I4? I4 was the bus current at 4 was all the branches were incoming, minus IB1 minus IB2 minus IB3. So now we will express the bus current as I1, I2, I3, I4. This is a 4 cross 1 matrix. Here we will have a 6 cross 1 matrix. IB1, IB2, IB3, IB4, IB5, IB6. Okay, like this. Now this is 6 cross 1. So the order of this matrix will be 4 cross 6. So now let us write first row 1, 4 and 6. That is 1, 0, 0, 1, 0, 1. Next is 2, 4 and 5. 0, 1, 0, minus 1, 1, 0. Then 3, 5 and 6. 0, 0, 1, 0, minus 1, minus 1. Then minus 1, 2 and 3, minus 1, minus 1, minus 1, 0, 0, 0. This, if you observe carefully, is actually A transpose. That means I bus, or let me delete this first. That means I bus is equal to A transpose into I branch. Now we know the relation between I branch and V branch. So I can write it as I bus as A transpose I branch. That is A transpose Y into V branch. And we can write as V branch as A into V bus. So that means I bus is equal to, since Y bus into V bus, here all elements represent matrices. So Y bus is equal to A transpose Y into A. Here Y is called as primitive admittance matrix. Okay, actually it is equal to Z primitive inverse, where Z primitive is primitive impedance matrix. So Z primitive is a matrix in terms of branch impedance, that is impedance of each and every transmission line. Now impedance of each and every transmission line will have two elements, Zs and Zm. Like in case of fault analysis, we will form a matrix something like this. Like this. Okay, diagonal elements will be self impedances and off diagonal will be mutual. So that is your Z primitive. We will take the inverse to find Y primitive, and then we will calculate A transpose into YA to find the Y bus. Here, due to this Zm, we can target the mutual impedance of the two transmission lines. So let us summarize what we covered in this lecture. We first saw what is the significance of Y bus and the Z bus matrices. Okay. Then we saw what is the each and every element of Y bus and Z bus represent. So that represented driving point admittance, transfer admittance, and driving point impedance and transfer impedance. We saw that Zii is not equal to 1 upon Yii, because one is defined under open circuit and other under short circuit. We saw Zii represent the Thevenin impedance of each and every branch. Then we saw direct inspection method, in which I told you that Y bus is a symmetric matrix, Y bus is a sparse matrix, and we calculated the percentage sparsity. We saw that diagonal elements are sum of the admittances, off diagonal are negative of the admittance between the two buses. Then the next method we saw was singular transformation method, in which we took care about the mutual impedances between the two transmission lines. And remember, the sum of the elements in a row is equal to admittance between the bus and the ground. In the next lecture, we will see some problems based on construction of the Y bus matrix.